the first video for week number 14. So let's look at what we call the mean value theorem. So we begin with this definition here. Let I be an interval and let f be a function from I to R. Then we say that f has a relative maximum. We say that f has a relative maximum at an interior point C of I if there exists some neighborhood. If there is some delta neighborhood of C such that f of x is less or equal to f of C for all x in the intersection of that neighborhood with I. Okay, so we say that f has a relative maximum at an interior point C in I if there exists a delta neighborhood V delta of C, okay, such that f of x is less or equal to f of C for all x in the intersection of the delta neighborhood V delta C with the I. Let me try to illustrate this by means of a picture. So let's assume maybe this is your function, something like this. For example, let's assume that's a graph of the function f. Assume this is your point C. Assume this is your point C. This one here. Okay. Then I can find a neighborhood here. Okay. Call it a delta neighborhood. If this is C, then this point will be C plus delta, and then the other point, this will be C plus delta. Okay. And then this other point, call it C minus delta. C minus delta. So this point is C plus delta. No, this point is C minus delta. This point is C plus delta. This point is C. Okay. So then you see f of C will be this one here. Now, if you pick an x inside this delta neighborhood, okay, for example, if you pick x here, then this will be f of x, which will be less than f of C. If you pick x here, all right, this will be f of x, which will be less than f of C. So f, we will say that f has a relative maximum at this point, okay, C, because f of x will be less or equal to f of C so long as x lies within this neighborhood here. Okay, so if x is inside the intersection of this neighborhood with I, here you can assume that, for example, this could be your I, or does not matter, you could start I from somewhere here up to there. So you take x in the intersection of the neighborhood and I. So long as x belongs to the intersection of the neighborhood and I, then f of x will be less or equal to f of C. If that happens, then we say f has a relative maximum at C. Now we say that f has a relative minimum at an interior point C of I if there is a neighborhood, okay, call it V gamma C of C such that f of x is bigger or equal to f of x for all x in the intersection of the gamma neighborhood of C and I. In terms of this diagram here, so if this is your C, right, then you can get a neighborhood here, for example, right? In this case, you see this will be f of C. If you pick an x here, then f of x will be bigger than f of C. If you pick an x here, f of x would be bigger than f of C. Okay, so f of x is bigger than or equal to f of c for all x in the intersection of the neighborhood with the I. So you'll get at least a neighborhood for which that is true. So if there exists a neighborhood for which that is true, then we say that f has a relative minimum at the point C. So next we have the interior extremum theorem. So this is what we have. Let C be an element in I. Let C be a point in I, which is an interior point, okay? And let f be a function that has a relative extremum at C, okay? You pick an interior point C in I, and f is a function on I which has a relative extremum at C. Now by relative extremum we mean it is either a relative maximum or a relative minimum, one of the two. Okay. Then if that's the case, then the derivative and if f is differentiable at C, okay, then the derivative of f at C must be 0. So let me explain this theorem again. If C is an interior point, okay, if C is an interior point of I, all right, and f has an extremum there, if C is an interior point at which f has an extremum, either a relative maximum or a relative minimum, okay? If C is an interior point at which f has a relative extremum, meaning it either has a relative maximum or a relative minimum there, and if f is differentiable at C, then the derivative of f at C must be equal to 0. Okay, so from this theorem we get this corollary, which says that let f be continuous on an interval I. Let f be a continuous function on an interval I, and suppose that f has a relative extremum at an interior point C of I, okay, then either the derivative of f at C does not exist or the derivative is equal to 0, okay, either the derivative does not exist or the derivative is equal to 0 at a point at which f has a relative extremum. So let's look at what we call the mean value theorem. It says the following. Suppose that f is a continuous function on a closed interval AB and that f is differentiable on the open interval AB, okay? Then there exists at least one point C in the open interval AB such that f of B minus f of A is equal to the value of the derivative of f at C times B minus A. So long as f is continuous on the closed interval AB and differentiable on the open interval AB, there will be at least one point C which sits inside the open interval AB such that f of B minus f of A will be equal to the value of the derivative of f at C times B minus A. That's what we call the mean value theorem. Now, if in particular f of A is equal to f of B is equal to 0, okay, then f of B minus f of A will be equal to 0. So you have that 0 is equal to the value of the derivative of f at C times B minus A. Now, since I is an interval, then B is bigger than A, so B minus A is not 0. But this product here is equal to 0. That means f prime C must be 0. So in that case, we get what we call Rolle's theorem. Okay, so Rolle's theorem tells you that if f is continuous on the closed interval AB and differentiable on the open interval AB, then there is at least one point C in the closed interval AB at which the derivative is 0. There is a point C in the open interval AB at which f prime C is equal to 0. That's what we call Rolle's theorem. It's a particular case of the mean value theorem. So I have the theorem here, which says that suppose that f is continuous on a closed interval AB and differentiable on the open interval AB if the value of the derivative of f at every point in I is equal to 0. That is, if f prime x is equal to 0 for all x in AB, right? Then f must be a constant function on I. That is, for all x in I, f of x must be equal to some constant k. So long as f is continuous on a closed interval AB and differentiable on the open interval AB, and if f prime of x is equal to 0 for all x in AB, then f must be a constant function on the interval AB. The proof is a short one, okay? We just have to prove that f of x is equal to f of a for all x in I. So to do that, let x be in the open interval AB, then for sure x is bigger than a, okay? So we simply apply the mean value theorem, okay, to the interval, the closed interval ax, okay? So if we apply the mean value theorem to the closed interval ax, then we obtain a point C in the open interval ax such that f of x minus f of a is equal to f prime at C times x minus a. But we know that f prime x is equal to 0 for all x in I, and since C is also in I, we have that f prime C is equal to 0. Now since f prime C is equal to 0, that means this is equal to 0, and therefore we have that f of x is equal to f of a. And if we set f of a to be equal to the constant k, then you have that f of x is equal to k for all x in I. So for this corollary here, we have f and g, which are continuous functions on the closed interval AB and differentiable on the open interval AB. If f prime x is equal to g prime x for all x in I, then there exists a constant k such that f of x minus g of x is equal to that constant k for all x in I. For the proof, you simply set h to be equal to f minus g, then the derivative of h, which is h prime, will be f prime minus g prime, okay? Now, since f prime is equal to g prime from here, okay, that tells you that h prime must be equal to 0. H prime must be equal to 0, and then the previous theorem tells you that h of x must be equal to k for all x in I. H of x must be equal to k for all x in I, and so you get this one here. For this definition, okay, we consider function f on I, then we say that that function is increasing. We say that that function is increasing on I if for every x1 and x2 in I, such that x1 is less than x2, it follows that f of x1 is less or equal to f of x2. We will say that f is decreasing on I if for every x1 and x2 in I, such that x1 is less than x2, it follows that f of x1 is bigger or equal to f of x2.